Hello, everyone. Our group focusing on the final project about extreme precipitation events. My name is Zhenqi, the first year MS PhD student.
I'm Lester Olivares. I'm a fourth year PhD student in geology.
And I'm Kyle Ruhl. I'm a junior in atmospheric sciences.
Cool. So this is the outline of our points this time today, and I will first introduction of some of the extreme precipitations. First, let's go to the definitions. Generally, there are two types of definitions, the relative and absolute one. The relative one is the standard precipitation index, and it is a relatively new George index based only on the precipitation. And it's an index based on the probability of precipitation for any time scale. So generally it is for the long time scale related to the ecology studies. And for short time studies, there are absolute threshold for the precipitation, like how many precipitation in 1 hour or 1 day. And then it's the precipitation datasets, studies of the past and the future change in the extreme precipitation in the mean state of the precipitation use the same original sources of weather and climate observations, including the in-situ observations using the rain gauge stations and remote sensing data and reanalysis data, and also some data can output from the climate model like the CMAP project. And then is the attribution. In summary, precipitation extremes are controlled by both thermodynamics and dynamic processes. As we know, the warming increases the atmospheric water holding capacity following the Clausius-Clapeyron relation, and then also the large-scale variability like the North Atlantic Oscillation, El Nino Oscillation, and some natural internal variability could also impact the extreme precipitation. And then in addition, the land use and the land coverage change, like the urbanization intensifies the extreme precipitations. And for the projection, it increases in the probability of extreme precipitation are non-linear and show large increases for rare events. But for the continent scale, as we focus on the South America, there are dipole patterns. For the northern South America, the extreme would change a lot, increase a lot with the increase of temperature, but for the south, it would not. So next, following the case study by the Cal.
So we're now going to look at a case study on extreme precipitation and energy balance response in the Horn of Africa. So the study of the Horn of Africa used long duration precipitation events during the rainy season, as opposed to short duration heavy extreme precipitation events, which we'll cover later in this video. The study ignored extreme precipitation in the drought seasons and focused only on relative extremes during the two rainy seasons in the Horn region, the March, April, May season, and the October, November, December season. The study also broke the Horn into 4 distinct biomes, forests, savannas, shrublands, and grasslands, and considered the effects of extreme precipitation on the energy budget in each biome as opposed to one total ecosystem. So moving on to the radiative forcings from albedo changes caused by long duration precipitation events, this figure shows the radiative forcings in watts per meter squared on the y-axis in each of the 4 biomes in the Horn of Africa. We observed that grasslands and shrublands experienced the greatest shortwave radiative forcings, ranging from 0.5 to 0.9 watts per meter squared, while forests and savannas, due to the strong opposing spectral changes between visible and near infrared albedo, exerted the smallest near zero surface shortwave radiative forcing during extreme wet events. When the 4 biomes were compiled together to represent one total climate, radiative forcings due to extreme precipitation events were found to be 0.33 watts per meter squared in March, April, May, and 0.31 watts per meter squared in October, November, and December. Next, taking a look at the plot of latent heat flux anomaly on the left. On the y-axis, we see latent heat flux anomaly for each of the 4 biomes on the x-axis. Here we see that for grasslands, savannas, and shrublands, on average, the latent heat flux anomaly increases in response to both albedo changes and the radiative fluxes from the extreme precipitation events. In comparison, the plot on the right shows that sensible heat flux anomaly on the y-axis for each biome, where sensible heat decreases in response to extreme precipitation. The March, April, May long rain season has greater anomalies than the October, November, December season. The effect in the forests is small in comparison to the other biomes in March, April, May, and it's about near zero in October, November, and December. Now we look at the radiation energy exchange anomalies. So in plot B on the top right, we see the incoming shortwave radiation anomaly during extreme precipitation events plotted on the y-axis in each biome on the x. We see that the shortwave radiation decreases for all biomes and seasons, ranging between -3 to -9 watts per meter squared. Below that plot, we have the outgoing long wave radiation anomaly during extreme precipitation events plotted on the y-axis for each biome on the x. Here we also see long wave radiation decrease in all seasons biomes, ranging from 3 to 7 watts per meter squared. Moving on to the plot on the left, we have the net radiation anomaly during the extreme precipitation events plotted on the y-axis for each of the 4 biomes. The net radiation anomaly is positive for all biomes, ranging from about 0 to 3 watts per meter squared, and this is more pronounced in the long rain seasons and in the grasslands and shrubland biomes. Finally, putting all the climate factors together, we can take a look at surface temperature change in each biome due to the long duration extreme precipitation events. This set of graphs shows the surface temperature change in degrees Celsius with the long rain season on the left and the short rain season on the right. On the y-axis is the observed change in surface temperature, and the x-axis is the standard precipitation index number, which is widely used to measure abnormal wetness or dryness, where a higher positive number indicates greater wetness. From the graphs, we observe in both seasons that surface temperature decreases in response to the net radiation increases and radiative forcings. We see that the higher the standard precipitation index, the bigger the difference, the bigger the decrease in surface temperature is. And in the Horn of Africa, we see that grasslands and shrublands have the greatest temperature decreases, while forests experience the least. So in sum, while this study gives us a good look at the energy balance impact of long duration extreme precipitation events, the exact extent of fluctuations and anomalies depends on biome, geography, and the precipitation intensity. Now we'll hand it over to Lester.
Hi, on my part of this talk, it's about an extreme rain event in the Atacama Desert. And this first figure just want to show how these floodings can destroy a kind of like a small city in northern Chile. So to tell you as a context, the Atacama Desert is in this area of South America, and it's a desert, so it usually rains almost nothing. In fact, as you can see in this figure, it rains less than 100 millimeters, and in the area that is going to be shown today, it usually rains around 30 millimeters per year. It is necessary to point out that this particular rain event, it happened in 3 days, and it rained in total 85 millimeters. Therefore, it can be considered an extreme rain event. Usually the area, it has been affected by winter rains that come from the south. However, this particular ones happened during March of 2015, which is southern hemisphere summer. Therefore, it was extremely rare, and it was uncommonly strong, considering that it rained over 80 millimeters in an area where it usually rains, I don't know, like regular rains are around 10 millimeters per event. So it was extremely rare. This happened due to an uncommonly warm Pacific Ocean that increased the temperature, and with that it could hold more water. So here you can see how air parcels can move southwards into the continent, holding more water, therefore creating this weird rain event. So as a conclusion, this particular rain event, it is due to like an unusually warm Pacific Ocean, and this particular rain event, which it is considered a century scale rain event, it might happen with more frequency in a context of global warming.